Okay, thank you. That makes a lot of sense. So then in theorem 2.13, where it's talking about the GCD, it's saying, for example, the GCD of M and N would be the product of primes where the power is the minimum of the power used in M and the power used in
Right.
N.
So suppose
Okay.
we take another number, like M equal to 147. So if you write 147 as a product of primes, let's see, that's 7 times 21, that's 3 times 7 squared, I believe. So V2 of 147 is 0. V3 of 147 is 1. V5 of 147 is 0. V7 of 147 is 2. Now we're looking at these two numbers and we want to find the greatest common divisor of M and N. That's the greatest common divisor of 120 and 147. So no power of 2 divides M. That can't be involved. 3 is okay. No power of 5 divides this. No power of 7 divides this. This is just equal to 3. 3 is the greatest common divisor of these two numbers. Suppose we compare this VP function for these two numbers. So V2 of 120 is 3. V2 of 147 is 0. So the minimum is 0. V3 of 120 is 1. V3 of 147 is 1. So the minimum is 1. V5 of 120 is 1. V5 of 147 is 0. So the minimum is 1. And V7 of 120 is 0. V7 of 147 is 1. The minimum of 0 and 1 is 0. Sorry, there should have been a 0 here. So the GCD of these two numbers is the product over all the primes of P to the minimum of VP of M VP of N, which in this case is the only time this is different from 0 is for the prime P equal to 3. You get 3 to the 1 or 3. So this is just a very important notation in algebra and number theory. We're not going to use it very much, but it's interesting to know if you read the chapter. I have to point out there's a lot more in each of these chapters than we're covering in the course. So basically what you're expected to know is what I cover in the lectures and what is involved with the various homework problems.
Professor? Hello?
Yeah.
So I had questions about the homework problem assignments. Problem 6, 8, and 12. Problem 6 is about extending the theorem 2.7, which is infinity of primes, to 4k plus 3 form.
Yes.
So, hello, can you hear? Okay, so for that problem, I mean, I saw you put up the lecture about the modulo M and the subclasses within Z, etc., right, or the partitions or whatever we want to call it. So my approach to that problem is because 2.7 is talking about all primes, while this problem is talking about subdividing primes into sort of like, two groups, 4k plus 1 primes, 4k plus 3, and then prime number 2. So essentially 3 groups, because any prime will be within those 3 groups. And my approach is to sort of like construct, assume that 4k plus 3 is finite, and then construct a number similar to what we did in the theorem 2.7, and show that any prime factor of that has to be 4k plus 3, and it doesn't belong to that set. Is that the approach that we are expected to sort of take?
So just for the benefit of everybody, let me sketch out a proof, which is very similar, I think, to what you just said. So problem, was this problem 10?
No, this is problem 6, which is extending the infinity of primes to 4k plus 3 primes. So
problem 6 in what section?
2.2, sorry, 2.2.
So
it says modify the
I understand. So
yeah.
Let me just say, for everyone's benefit, I would suggest when you look at an assignment, you always look at the latest version of the notes that I've posted. So I had posted a new version of the text in which I added some problems. So the problem that you're asking me about, which is an excellent problem, I'm going to do it, was not part of the homework assignment. It was problem 6 in the old version of the notes, and not problem 6 in the current version of the notes. But
I was looking at the book that you uploaded, the 600-page book.
It's under constant change. So
okay.
If you go to the website, you'll see it'll have the textbook and the date of the latest version. So the original 600 pages or so I replaced with a corrected version, because as we go through, I see things that need to be changed and improved and corrected. But that's okay. The problem you asked is a very good problem, and it gives me an excuse to do it because it's an important problem. So the problem, which I can state as a theorem, is there exist infinitely many primes of the form 4k plus 3. So just to understand that a little more clearly, suppose we start to write out the primes. There's only one even prime, which is 2. And then every other prime has to be an odd number. If you take an odd number and divide it by 4, you get a remainder of 1 or 3. So as we look at the primes, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, and so forth, this number, if you divide it by 4, leaves a remainder of 3. If you divide 5 by 4, you get a remainder of 1. If you divide 7 by 4, you get a remainder of 3. So you can look at all the primes and see what is the remainder when you divide by 4. And we get a fair number that leave a remainder of 3. I'll cross out 2 because it's even. All the others leave a remainder of 1. And the idea is to prove that there are infinitely many primes of this form. We know there are infinitely many odd primes. Some of them are of the form 4k plus 1. The others are of the form 4k plus 3. And I want to show in this special case, or it's a very important case, there are infinitely many primes of the form 4k plus 3. So this requires a modification of the proof of the fundamental theorem of arithmetic. So let's recall how we proved a modification of the proof of not the fundamental theorem of arithmetic, but of Euclid's theorem that there are infinitely many primes. And the way we proved Euclid's theorem was if we took a finite collection of primes and we multiply them together and add 1, we have a number n, and n must be divisible by a prime q different from P1, P2, up to Pk. So if I have any finite set of primes, I can prove, Euclid proved, that there must be a prime in addition to those. So if there are only finitely many primes, there would be no other prime, and that would be a contradiction. So the question is, how can we modify this? And the clever idea that someone had long ago was to observe if you take an odd number of the form 4k plus 1 and an odd number of the form 4l plus 1. So this is two numbers that when you divide them by 4 leave a remainder of 1. If you multiply these two numbers together, you get 16kl plus 4k plus 4l plus 1, which is 4 times the integer 4kl plus k plus l plus 1. So this is 4 times some number m plus 1. So this says that a product of numbers that have a remainder of 1 when you divide by 4 is another number that has a remainder of 1 when you divide by 4. So the way to think of this is that if n is odd, and n is a number of the form 4k plus 3, when you write n as a product of primes, they're all going to be odd. Then if you write n as p1, p2, up to p sub r, so this is some product of r primes, at least one of these primes, p sub I, is of the form 4l plus 3. Because if each of these primes was of the form 4l plus 1, when you multiply them together, you get another number of the form 4l plus 1. So if a number leaves a divisor, a remainder of 3 when you divide by 4, and you write that number as a product of primes, one of those primes must be of the form, must have a remainder of 3 when you divide by 4. So now here's how we modify Euclid. Let P1, P2, up to, let's say, P sub k be primes of the form 4i plus 3. So these are all primes that leave a remainder of 3 when you divide by 4. And now let n be the number you get by multiplying these primes together. Multiply that by 4 and subtract 1. Or, if you like, multiply them together.
Or add 3.
And add 3.
Mm-hmm.
So this is a number of the form 4 times something plus 3. And we write it as a product of primes, Q1, Q2 up to Q sub S. And one of these primes, actually, it's better to write it as this minus 1.
Well, I think you can write it as 3, but then explicitly rule out 3 as a prime factor.
Right, you can. So let's just write it as
Right.
minus 1, because a
clear.
number of the form 4 times something minus 1 is of the form 4 times something else plus 3. If you have 4u minus 1, that's 4 times u minus 1 plus 3. So every number of the form 4 times something minus 1 is 4 times something else plus 3. So this number, when you divide by 4, gives you a remainder of 3. You write this number as a product of primes. None of these primes can be equal to one of the p's, because if they were equal, that prime would divide 1. So each of the primes q sub I is different from the primes p sub j. But one, at least, is of the form for v plus 3. One of these primes leaves a remainder of 3 when you divide by 4. It's different from these. So for every set of primes of the form 4k plus 3, every finite set, there's yet another one. So the number of primes of this form has to be infinite. That is the proof. That is a proof.
So, no, I mean, I got that. So my question was basically that we can use that modulus principle that, 2 4k plus 1 will always end up as a 4k plus 1. And it'll work for 6k plus 1 as well, etc.
I'm sorry, what is it that you're saying?
So that's exactly what I was asking. But my question was, we can use the concept that, if you have two numbers of 4k plus 1 time, when you multiply them, they will result in another 4k plus 1 number. We can use that principle to rule out, to do this. That was going to be
you can use that principle, or just as I did here, you can just write it down and give the one-line proof, basically. But you can certainly use the language of congruences if you wish.
Okay. I have another question, unless somebody else has a question.
Huh? Yeah, we're dividing by 4. Someone asked, why are we dividing by 4? And it's because we're looking at numbers of the form 4k plus 1 and 4k plus 3. And I will post the missing problem sessions that I have, or the videos, as soon as we finish online right now.
I have another question, unless somebody else has a question. Hello?
Yep, go ahead.
Okay. So no, I was just making sure that nobody else had a question, because I don't want to hog up the time. The other question I had was about the Frobenius numbers. So I can.
So I did not intend to ask any questions about the Frobenius numbers. So that must be because you weren't looking at the most recent version of the text. But I'm happy to answer such a question if you want.
Well, I mean, to be honest, I kind of did almost all the 2.2 based on the old version, and then
that's
I was
fine.
looking at
if you did that, you learned a lot. That's great.
So the new question 13, it was a question 12 over in the older version, where it says that prove that the Frobenius Frobenius number is A1 minus 1 times A2 minus 1. So I could figure that part out, that why it has to be basically A1 minus 1, A2 minus 1, because one is GCD, and if the two multipliers for A1 and A2 have to be, maximum value can be only 1 minus each of them. So the A1 minus 1, A2 minus 1 gives you the Frobenius number for A1 and A2. I get that part. The part I couldn't figure out is the second part, where it says that, basically half the numbers below Frobenius numbers can be expressed as a linear combination, and half cannot. So I was hoping that you can elaborate a little bit on that.
Yeah, so that I don't want it to get into now, because that will truly take up a half an hour or more of time. So if
Okay.
you send me an email privately so I don't forget, I will write out the solution and show it and send it to you.
Okay, all right. No, I'll do that. And last question about the question 6 in the newer version, which says let R be greater than or equal to 2 for every positive integer n. Let d sub R n.
What section is that?
Again, 2.2. I'm looking at 2.2.
Okay.
So it says that drn is a ordered factorization of n into r parts, r tuple a1 to ar of positive integers, n is equal to a1 to ar. And then it says prove that n is prime only if drn is equal to r. And if n is composite, if and only if drn is greater than r times r plus 1 by 2. So here basically, let's say if we have a factor, a number like 5, which is a prime, and let's say r is 3. So that means we're supposed to have, let's say.
So read the problem again, please.
Sure. It says let r be greater than 2, greater than or equal to 2. For every positive integer n, let dr in parentheses n, the function drn, denote the number of ordered factorizations of n into r parts, that is number of r tuples a1 up to ar of positive integers, such that n is basically a product of a1 to ar. And then it says that dr hat n denote the number of r tuples of positive integers. I think it just repeats itself on that one, of ai greater than 1 for all i 1 to r. So basically ai can go from 1 to r.
Okay, so in the latest version of the notes, which I hope I posted, that's the one I'm looking at, this is problem number 9, but that's okay. So dr of n is the number of ordered factorizations of n into r parts. And the hat r of n is the number of unordered factorizations, or, okay. Prove that n is prime if and only if dr of n is equal to r. So if you're going to write a number as a product of positive integers, if it's prime and you're going to use r of them.
So does that mean that if I'm writing, let's say 5 as a product of 4 numbers, it's going to be like 1 times 5 times 1 times 1? So there's,
right. So for example, if we have r equal to 3 and n equal to 5,
right,
and the number of ordered factorizations of 5 is, you can write 5 as 5 times 1 times 1, or
Okay.
1 times 5 times 1, or 1
Right.
times 1 times 5, and those are the only ways to do it. And in general,
So
for
I
any
thought that
prime, that's the situation. So d sub r of a prime is equal to r if p
RC1.
is prime. Because basically it's like
Right.
you have r boxes and you
Yeah,
want to
it's
put down
basically
integers where the product is equal to the number.
right.
Well, if the number is a prime, you have r choices for where to put the prime, and everywhere else has to be a 1.
Understood. So I mean, I figured that you know that's basically the R combination one. That's why it's R. It's the if and only if part that I was wondering, like, how do you prove the backwards? That if
Okay,
it's only
so
R combination,
so
it has
this
to be a
says
prime.
that p prime, or a number n, is prime, implies d sub r of n equals r. Let's prove the converse. D sub r of n equals r implies n is prime. So the way to prove it is actually almost part of the problem. Suppose if n is composite, so n equals a
Okay.
times b, which is
Also, you
some,
prove that then dr of n is going to be n plus 1 by 2 at least, and not n.
so let me finish. So
Okay.
if n equal a times b is composite, where a is at least 2 and b is at least 2, we have to distinguish two cases. So in the first case, A is different from B. So in this case, you can think of this as you have R boxes, you pick one where you put A, and you pick another where you put B, and you can choose those R boxes in
RC2 fashion.
choose two ways, R
Right.
minus 1 over 2. In addition, you can also put
Put the
n in
number
one of
in.
those boxes, and you have r ways to do that. And
Okay.
r times r minus 1 over 2 plus r is r times r plus 1 over 2. The only special case is when a equals b. So if n equals a squared, and again, the only time you cannot, if n is a squared, the only time where you can't write this as a product of two different numbers is in fact when n is p squared. So if n is a prime, if n is the square of a prime, then the situation is, actually, it doesn't make any difference.
Well,
You
you
can
have to
still
do
choose two places
32
where you
divided by
put
2
your a
factor,
and
right?
your b, and it's fine.
So it should be n minus 1 over 4 in that case.
Excuse me?
If n is prime squared, then wouldn't RC2 R choose 2 replaced by R choose 2 divided by 2 factorial?
Well, what I'm in the problem, it only says to prove the lower bound. What you're telling me is what you think dr of n is when n is equal to exactly when n is p squared. And when n is p squared, it's exactly equal to this.
Right. No, I'm not sure about that, Professor. I mean, I thought that was correct, but then when you mentioned the p square example, so if when a is equal to b, wouldn't that cut down the number of combinations by half for the first part? It wouldn't
Well,
be n
let's look at an
over.
example. So suppose n is 4, which is 2 squared, and r is 3. So we can have 4, 1, 1, 1, 4, 1, 1, 1, 4. We can also have 2, 2, 1, 2, 1, 2, 1, 2, 2. All right. Those are the only possibilities. 6. So
Right.
D3 of 4 is 6, and which is 3 times 3 plus 1 over 2. So it's exactly that.
Okay. Okay. Makes sense. I'll think it through again.
Anyone else have a question? So the one thing that you will have noticed is that as we go from 1 week to the next, and in summer school, from 1 week to the next means from 1 day to the next, because every day we cover a week's work. The level of abstraction and the kind of mathematical reasoning being required and expected goes up. So in the course of this semester, there will be a lot of new ideas and new concepts, and it always takes a lot of time to learn them. And it's hard to compress that, but when you choose to take a course in summer school, you somehow have to figure out what to do. So if you look at the last lecture that I posted, I think it's lecture 6, I've introduced the definition of a group. That's a concrete concept, and it's also an abstract concept. And you need to really spend a lot of time wrapping your head around this notion of a group and some things related to a group that we will see soon, which are called subgroups and quotient groups. And the best example, or the core example of this, is if you take the group of integers, you look at all the multiples of some number like 2, we'll show that's a subgroup, and the quotient group is the group of congruence classes. So there will be a lot of new material to master over the long weekend.
So, Professor, in terms of your textbook, should I be using the textbook that says revised July 14, or should I be using the chapter 2?
Oh, no, always use, and actually I'm going to put up, I don't think I put up maybe the last revision. So that's why there is some confusion about the homework problems. But because I changed it and I made the homework problems a little bit easier. As I put in some easier problems, and those are the ones that I assigned. So sometime this afternoon, I will upload the July 16 version of the textbook. And that's the one you should look at.
Okay.
Everything in the 2 chapters I posted earlier and the earlier versions of the book, it's all correct. It's all excellent mathematics. It's all good stuff to know. But what is required for this course, I say, is what is in the lectures and the homework problems.
Okay, so I should wait until you post a newer version to look at the 3.1, etc.
Yeah,
because
I'll do that within 10 minutes of logging off of this problem session.
Okay, no problem. Thank you.
And Professor, to be clear, the July 16 version of the textbook will have the proper homework questions?
Yes, I mean, all I did was I added some easier homework problems the other night, and those are the ones I assigned. But I guess I didn't upload that version yet, so I'll do that immediately after we log off.
Thank you.
Anything else? Anyone else have a question? All right, so remember, we reconvene for anyone who wants this afternoon at 4 o'clock. And I will immediately put up the latest and best version of the text. Bye,
Thank you.
everybody.
Bye.
Okay, thanks, Professor. Goodbye.